Hydrogen is poised to play a key role in our energy future. It is currently used as a feedstock for fertilizer production, to produce materials for construction, such as steel manufacturing, synthesis of chemicals, and as an energy storage medium that can be used to create on-demand electricity. Approximately 100 million tons of hydrogen were consumed globally in 2023. By some estimates, the annual consumption of hydrogen will reach 600 million tons by 2050, as it will act as a vital green energy carrier. A major challenge is that 99% of hydrogen is currently produced using fossil fuels, primarily using steam methane reforming. This gray hydrogen leads to significant CO2 emissions and indicates an area that must be drastically decarbonized if we are to reach our net zero climate goals by 2050. Renewable electricity from wind and solar can be used to produce so-called green hydrogen, free of any greenhouse gas emissions during production and utilization. Such electrolysis processes use renewable electrons to split water into its component parts, hydrogen and oxygen. Electrolysis technologies must be able to operate intermittently and for long periods of time in order to take advantage of cheap, renewable electricity. In order to be scalable, they also need to avoid the use of critical rare earth metals to catalyze the water splitting reaction. Anion exchange membrane, or AEM, water electrolysis is an extremely promising technology for green hydrogen production. Using membranes and electrodes assembled in a cell stack, AEM electrolyzers can efficiently produce a stream of hydrogen from the simple inputs of water and electricity. AEMs are a critical component in this process, as they dictate the efficiency and durability of the device. Through technology developed in the lab of Dr. Shile Hu at EPFL in Lausanne, NovaMea is commercializing novel AEMs and electrodes to make scaled green hydrogen a reality. The Innomem program has provided a boost to this technology scaling through the project titled Scaled Up Manufacture of Membranes and Ionomers for the Energy Transition, or SUMMIT. Through this project, NovaMea has teamed up with the University of Duisburg-Essen to overcome critical challenges associated with bringing their membrane from the lab to the industrial scale. These include the use of different solvents for membrane casting, adding a reinforcement layer to improve the mechanical stability of the material, and optimizing parameters for a pilot-scale roll-to-roll casting machine. Through intensive lab experiments and analysis, as well as feedback provided by NovaMea, researchers at the University of Duisburg-Essen have worked to optimize the casting process for the membrane. Factors such as polymer concentration, type of solvent, and speed of the casting blade play an important role in resulting membrane quality. In addition, they have tested various support materials and methods to reinforce the membrane and provide high levels of polymer penetration in the reinforcing layer pores. Finally, they have taken the findings from the lab to the pilot casting facilities in Duisburg. This video demonstrates how the casting process can be scaled up to a 20 centimeter width roll, and that solving the challenges at the pilot scale can enable a higher technology readiness level and motivate the push towards larger scale commercialization. With the successful completion of the Innomem project, NovaMea has the foundational knowledge needed to cast high-quality membranes in a roll-to-roll machine at a relevant scale for its clients.